All right, welcome to The Explainer. Today we're going to tackle one of the biggest, most profound ideas in all of science, Albert Einstein's general theory of relativity. And look, this isn't just some small update to our understanding of gravity. Oh no, it is a complete reimagining of the very fabric of the universe. So yeah, let's dive right in.
Let's start with a really weird question. What if that feeling of being planted in your chair right now has absolutely nothing to do with a force pulling you down? What if gravity isn't a pull at all? I know it sounds crazy, but this one idea, this is the key to unlocking Einstein's entire universe. You know, for centuries, the universe basically ran on Isaac Newton's rules. He saw gravity as this mysterious, invisible force that just acted instantly across any distance. The sun pulls on the earth pulls on you. Simple. But then came Einstein with something way more radical. He said gravity isn't a force, it's a feature of the universe. It's the geometry, the actual shape of space and time all woven together.
So you might be asking, why the huge change? I mean, Newton's theory worked great for over 200 years. It predicted tides, planetary orbits, you name it. So what broke it? Well, funny enough, Einstein himself broke it. The key word here is instantaneously. In Newton's world, if the sun were to just, poof, vanish, the Earth would instantly know. It would fly off its orbit in that exact moment. That gravitational tug would disappear across 93 million miles in literally zero time. It's what they call action at a distance.
But see, here's the problem. 10 years before general relativity, back in 1905, Einstein published his theory of special relativity. And its number one unbreakable rule is that nothing, not an object, not information, not a force, nothing can travel faster than the speed of light.
And boom, there it is. A massive paradox. How could Newton's instantaneous gravity be right if special relativity's cosmic speed limit was also right? They just can't both be true. The news that the sun had vanished couldn't possibly reach Earth instantly, so physics was in crisis, and a totally new theory of gravity was needed.
Now, to solve this, Einstein didn't just lock himself in a room with a bunch of equations, not at first anyway. He started with a thought experiment, something he later called the happiest thought of my life, and it led him to this incredible new principle.
And this is it, the equivalence principle. Just imagine you're in an elevator, way out in deep space, far from any gravity. If that elevator starts accelerating upwards, you're going to feel pressed to the floor, right? Just like gravity. Now flip it. Imagine you're in that same elevator back on Earth, and the cable snaps. As you fall, you'd be totally weightless, just floating, exactly as if you're in deep space. So the big insight is, from your perspective, gravity and acceleration feel identical. And for Einstein, if they feel the same, maybe they are the same.
Okay, so if gravity is just acceleration, why do planets move in circles, in these curved orbits? Well, let's use an analogy. Think about the shortest distance between two cities on a flat map. It's a perfectly straight line, of course. But the Earth isn't flat. If you actually fly that route, your path across the surface of the globe is a curve. The pilot is flying in a straight line, the straightest possible path, but they're doing it through a curved space. That path has a name. It's called a geodesic. And Einstein realized that's exactly what planets are doing. They are moving in the straightest possible lines through a universe that is itself curved. This idea is perfectly captured in this classic quote from the physicist John Archibald Wheeler. Think of space-time like a big stretched-out trampoline. If you put a heavy bowling ball, that's our sun, in the middle, it's going to create a big dip, a curve in the fabric. That's the first part. Mass tells space-time how to curve. Then if you roll a little marble, our Earth, nearby, what does it do? It follows the curve made by the bowling ball. It's not being pulled, its path is just determined by the shape of the trampoline. And that's the second part. Curved space-time tells mass how to move. Okay, so this is a beautiful, elegant picture of the universe, for sure. But for a theory to be actual science, it has to make predictions that we can go out and test. And let me tell you, general relativity's predictions were some of the most mind-bending in the history of physics. The very first big win for the theory came from a really annoying cosmic mystery. For decades, astronomers knew that the orbit of Mercury wasn't quite right. It wobbled, or precessed, just a tiny bit more than Newton's physics could explain. It was a super small error, but it was always there. So when Einstein ran the numbers using his new equations, they predicted an extra little orbital shift of exactly 43 arcseconds per century.
That was the precise amount that had been baffling everyone. It was a perfect match. And it was the first huge piece of evidence that he was onto something incredible.
And the hits just kept on coming. The theory predicted that a huge object like the sun should literally bend the path of starlight passing by it. That's gravitational lensing, and it was confirmed in 1919. It predicted that time itself runs slower in stronger gravity. We call that gravitational time dilation, and we've proven it with hyper-accurate atomic clocks. And it even predicted the existence of things straight out of science fiction. Black holes, places where space-time is so curved that nothing escapes, and even gravitational waves, actual ripples in space-time, which we finally detected 100 years later in 2015.
Now, I know what you're thinking. Black holes, ripples in the cosmos, it can all feel pretty out there, pretty abstract. But I can absolutely guarantee you that you use this theory, this idea of curved space-time, probably every single day.
In fact, there's a piece of technology that millions, maybe billions of us rely on that simply would not work if we didn't account for the strange effects predicted by general relativity.
That's right, your phone's GPS, your car's navigation. It's a daily test of Einstein's theory. The satellites that make GPS work are orbiting high above us in a region of weaker gravity. And because of time dilation, their clocks actually tick a tiny bit faster than our clocks down here on Earth. I mean, it's a tiny, tiny fraction of a second, but it adds up. Over a single day, that error would throw your GPS location off by about 7 miles. The entire system only works because the software is programmed to correct for Einstein's curved spacetime.
So there you have it. From the weird wobble of Mercury's orbit all the way to the map on your phone, general relativity describes our universe with breathtaking accuracy. It completely replaced the old idea of gravity as a force with this incredible image of a dynamic, curved fabric of spacetime. And that really leaves us with a final, profound thought. If the universe is a fabric, shaped and warped by everything in it, what other secrets, things like dark matter and dark energy, might we find woven into its design?